sharing my web page. I'd like you all to go to your avenue to learn if you could. Okay, and today is a very interesting, I hope it's interesting. You guys say, yeah, interesting, Eugene. So if you go to content, have you done the illegal stuff of downloading the textbook, yes or no? Yes, good. I love doing illegal stuff. And I have put down here, can you download Unforced Mechanical Vibration System? And it's a, holy, how did it do that? Download as a software, it's on Excel. Okay, if you could download, can you do that? Or have you done that? Okay, some of you not done that, is fine. Okay, so I'll show you what this is all about. Okay, and what today's lecture, I hope today's lecture, I could cover this amount. Okay. Right. So what you see over here, okay, is a response graph, which you have, I hope you all can see the words, which you have time, okay, on the x-axis, and on the y-axis is amplitude, okay, and if it's a blue line, it's over damping, and is a yellow line is under damping, okay. So let's say if you have to design, you have designed a system, okay, and the spring and damper are fixed. Okay, so you have, so for example, you buy a car. I need to use the example of a car, but it's the most straightforward example to use. You have a car, okay, and this is the stiffness that you have done. That you have set up. The stiffness of the spring is 700 Newton per meter. The damper is at 200 Newton second per meter. And then the weight is 14 kilogram. Okay? Then you might want to what? Lighten up the car. Okay, so you want to lighten up the car and you reduce the car weight by down to 9 kilogram. Can you see how the system move, right? So if I change to, what was it, 11 or 14 before, right? You can see the graph shift, okay? And all this shifting of graph is not magic, but it's all what? Mathematical expression, which today I will teach you what is it all about, how to express a mathematical equation. Okay, now all of a sudden, you decide to put more fuel into your car, right? You need to add more gas into your car. So after you add more gas, maybe you add 30 liters of gas, assuming it to be 30 kilogram. What happened to your system? Can you see what's going on? Yes or no? If I reduce the weight to what? To 11 kilogram or 14 kilogram like before, okay, you have what? Over them, the blue line. Okay, then now we increase the weight, okay, by putting gas whatsoever, you get 30 kilogram. Okay, you get, what do you see now? You have something known as an oscillation. Yes or no? Is this good or bad? Anyone? Yeah. Why? You're right, it's bad. Okay, it's bad. I try to convince you why. So for example, if this is the car, right? When you are taking a corner, what do you want your tires to be? Fully in contact with the what? With the road. Yes or no? Right? Fully in contact. But if you have the oscillation, what will happen? Your car will what? So every time you jump, do you have contact? In jumping is created, but you have had what? Oscillation. That is why, how many of you have been in a sports car before? Can be second hand, third hand, I don't care. Could you imagine riding a sports car from here to Montreal? What will happen to your body? I know what will happen to mine. I will just go like I will ache everywhere because I'm always like the car is not absorbing the vibration, but who will be absorbing the vibration? Are we clear? Okay. So today we are going to the physics behind it, okay, and the math behind it. Okay. How to predict oscillation like this. Oh, yeah, it's a predictive model. Okay. So we go from there. So we will work our example on this. Okay. I'll explain the physics, the math, then we go into this Excel spreadsheet. Are we clear? Okay. And I hope I understand that I have until what, 11:20 with you. Am I right? I promise to stop at 11:10. How's that? Okay, so no break. We go up to 11:10. Okay, here we go. Right, so yesterday, what we briefly look at, okay, so if I could recap slowly, okay, what we briefly look at is I drew, this is just a recap, okay, just to what happened on Wednesday. So on Wednesday, we asked the question, what is stiffness? Okay, what is stiffness? So what I've related, if I've drawn a spring, right? I've drawn a spring, and this spring has a motion y, been pulled down y. And what we have over here, we have a response. And based on the amount of force we put in, okay, the y and over here the f, okay, we have a response like this. So this is linear. I'm going to draw it linear. So if it's linear, draw linear. And I highlight that over here, there's this gradient, and this gradient is basically delta f over delta y. Okay, so this gradient, which I label it as k, small k, not big K. Okay, so small k is equal to delta f over delta y, and we can write this out as f is equal to ky. Okay, and the definition I wrote it yesterday, but I will define over here k is known as the what? Stiffness. And this is in Newton per meter. Now, as you can see, not everything look like a spring. Okay. Okay. So this is what I call a schematic. Okay. This is called a schematic. Pardon me. I found a lead on my. So the next thing we are going to relate is we're going to relate to the real world. Okay. How is this related to the real world? So in the real world, we have what we call tensile test configuration. You can start copying from here, okay? In a tensile test configuration, the system is under axial loading. Okay? So in axial loading, this is your structure. And then what I will draw over here, this is my centroid. Okay. So at the centroid, from a distance, oh, too thick. We have a distance from here to here. This is our L naught. And over here, this we have a cross-sectional area. Okay. And from here, what we have now is when we apply a force, the thing extends itself. And this force is applied at the centroid. Okay, this force over here is applied at the centroid, and I will use the same nomenclature. I'll use the word F. Okay, so what we have now over here is we have a distance L1, and the distance from here to here is our delta L. Okay, so this behaves like a spring, right? So why do I say that? If we were to stare, or if we were to look at the previous graph, okay, if we were to extend we were to put a force onto it, what will happen is the spring will also what? Extend. So you will have also the same delta L over here. Okay. However, if we were, because what we are talking about here is a what? It's a system that is known as a tensile test configuration. In a tensile test, you measure the force and you measure the what? Displacement. So what we usually relate this to is under the elastic region. Okay, under the elastic region, the material will behave under Hooke's law. Okay. Now, what do we mean by elastic region? Anyone? When I say elastic, what does it mean? Yes. Yeah. In the elastic region in materials, in mechanical properties is what? When you release the load, what will happen to the material? It goes back to the what? Original position. Question for you. If I stretch a spring and I let go, what happened to the spring? It goes back to the original what? Position. Now you could relate, yes or no? Okay. So from here, you have a linear relationship. Okay. And then over here, we have what? Change in stress. And then we have change in strain. And over here, this is known as our E, which goes into what? Okay. Now, can you see the difference with the graph at the top and the graph at the bottom? There are differences and there are similarities. Can you see that? There's a relationship, right? Yes or no? Oh, look, but see nothing. Yes or no? Can you see? Yes. Right? You can see something, right? Right? So we know that stress is equal to force divided by what? Area. And we know strain is equal to what? Delta Y over Y original. This over here is also equal to your change in what? Change in Y. Okay, so you can see some similarity. So from here, we know that relationship based on Hooke's law. Okay, so from Hooke's law. Now, if you have any question, because I'm writing, I'm not looking at you, you can just say, excuse me, okay? in a gentle way or not, I will jump. Are we clear? Okay, don't hold back. Okay. I mean, don't hold back means don't make me jump also. Okay. So from Hooke's law, we know that stress is equal to E multiplied by epsilon. And then we also know the relationship that stress is equal to force divided by area. And we are also aware that the strain, that strain, okay, epsilon, is equal to change in the length divided by what? L naught. Okay. So we substitute the above into Hooke's law.